Hello everyone. My name is Esha Sarkar and I'm here today to talk about our work I Came, I Saw, I Have, which deals with automated generation of process-independent attacks for industrial control systems. This work is a collaboration between myself, Hajar bin Krauda, and my advisor, Mihalis Maniataku. Now, what is industrial control systems and why do we care about its security? Industrial control systems is a subset of cyber physical systems where the physical processes are sensed, evaluated, and controlled by programmable controllers, but in large industrial settings. These sensors, the controllers, and actuators follow physical values and processes. Therefore, there is less human error and more throughput. Because of the scale of the systems, they are closely related to national infrastructure, the national finance, and even human lives. Therefore, they're deployed in many critical infrastructures. The Department of Homeland Security in the United States actually enlists 16 such infrastructures like water, chemical, nuclear power plants, which are again largely a part of ICS. However, they are not traditionally designed to handle security threats. At most, they are air-gapped from the enterprise network as a security measure so that these devices are not easily accessible to the attackers. Because of this reason, they have been subjected to many real-world attacks with or without network access. For example, in the year 2000, a SCADA attack performed by a disgruntled employee led to a sewage contamination. In 2008, one IoT device was attacked to cause an oil spill by another IoT device. But perhaps the most impactful attack was caused by Stuxnet, which was a malware which attacked Iran's nuclear power plants and maliciously manipulated the controllers so that the centrifuges controlled by those controllers rotated at very high speeds and self-destroyed them. This particular attack actually led to a worldwide awareness and everybody started thinking about security of ICSs. But even then, there were attacks in 2016 on energy ICSs and also in 2016 on Ukrainian power grid, which led to power outages. In 2017 as well, there were some attacks on Schneider Electric power plant. All of these attacks sort of reinstate the fact that there are various entry points for an ICS, not just the network. And each of this attack actually manipulated the critical infrastructure. But again, these attacks are also specific to that particular ICS, if not that particular plant, which leads to a largely unexplored vulnerability for ICS, which is our research question, which is it possible for a malware to automatically generate attacks without targeted knowledge? Naturally, the malware would have to gain targeted knowledge, and which we perform using machine learning. The ICS reconnaissance is performed in two stages, which we call as ICS sector fingerprinting, which gives a broader idea about the plant, and ICS process fingerprinting, which gives us the fine-grained idea about the plant. After the targeted knowledge is extracted by the malware, we explore perturbation-based attack design, where the malicious manipulation is the perturbation aimed by the attacker. After we demonstrate our pipeline, we perform an end-to-end study on a benchmark ICS, which is the Tennessee Eastman, to showcase that our attacks are in fact possible on hardware-in-the-loop test beds. To understand the threat model, let us look at a typical ICS layout and the assumptions for the attacker. We assume that the attacker is able to inject the infected code or infected malware in one PC. This particular attack model has been used in real world attacks as well, and attackers have used social engineering, infected USB sticks to infect that particular PC. After the malware is injected, the malware travels laterally till the point it reaches a machine which hosts the HMI or the SCADA. It takes the screenshot of that particular HMI and performs ICS sector fingerprinting to get a broader idea of the plant. After it has achieved the broader idea about the plant, it connects to the PLC and extracts the PLC code and analyzes it to get more idea about the ICS process, which we call as the ICS process fingerprinting. Now the malware knows the targeted knowledge about the plant, and it generates the attack vectors which can lead the plant to a suboptimal state. The generated attack vectors are injected back into the PLC code, and now the infected PLC code propagates actuating signals to the actuators and the sensors and the other field devices to perform the attack, that is to run the plant into a suboptimal state. Now let us see the first step of the plant reconnaissance, which is known as the ICS sector fingerprinting. We perform this classification using machine learning, and to build the model, we needed a data set which was not available to us. And therefore, we started with a data set collection of HMI snapshots. We looked into the general purpose search engines like Google, Bing, and Flickr, and also IoT specific search engines like Shodan to get the HMI screenshots. We also went into popular companies' manuals to see if we could find some HMI screenshot or SCADA screenshots in them. Using them, we categorized all those screenshots into 16 categories, which were given by Department of Homeland Security critical infrastructures. But 6 of those categories could not have had HMIs because they were related to government operations. 7 of those sectors had HMIs, but they were very small in number, less than 10. 3 of those sectors were found to have HMIs more than 100. But for classification, that is the annotation, we actually divided the data set in such a way that the classification belonged to those 3 sectors. We analyzed the objects, the images, the text from the images, some metadata that came along with the images to perform manual annotation. For getting the final data set out, we saw that 95% of those downloaded images were not usable, and mostly were thumbnails, some logos, some advertisements, and also they were of poor resolution, so we could not use all the images for image annotation. Further, there were some images which were extremely small in size, and we could not use them because they did not give any generic information about that sector. With all these challenges, we were able to find 3 broad sectors where these HMI screenshots belonged, and also it helped us because these 3 sectors were the most attacked sectors in our real world. But there were certain challenges in building these classifiers. For example, the data set, even after having 100 images per sector, was very small, and we could not have used a very deep network. Again, the features of those images were not robust enough. They were not distinguishing enough. And therefore, we had to build a deeper architecture for that. To represent these problems, we present 9 images from our constructed data set. We see striking similarities between samples of different classes and differences between samples of same class. Because of this, we saw there was a lot of overfitting in our custom DNNs, but a good observation was that as we increase the number of layers, making a deeper architecture, the test accuracy actually improved. For solving the small dataset problem, we use data augmentation, where a perturbed version of our dataset would be available for training in each iteration. Further, we use dropout layers to reduce the overfitting so that the neurons do not get co-adapted and they learn independently. And for using a deep network without having to train it, we used transfer learning, where the robust features were extracted using the pre-trained network, and we used 3 custom layers to be fitted to more to our problem. Using these, we were able to improve our accuracy by almost 10% to around 80.91%, around 10% more than what we were getting using our custom DNNs. But it was still low, and we could not have performed an attack, a full-fledged attack using this value. So we saw that a lot of the images had a lot of text pertaining to that sector, which gave information about that sector. Therefore, we used optical character recognition to extract that text, those text snippets from those HMI screenshots. Then we translated them into English and removed any special characters or numbers which were primarily sensor values which did not give any information about that sector. We used a feature extraction method which used the top 2000 features using mutual information. And finally, we used a multinomial knife-based classifier which gave our final prediction. Using text-based classification, we got 3% higher class test accuracy. But we thought that is it possible to improve it further? To improve it, we stitched these two classifiers together. We took an HMI screenshot and ran it through the pixel-based classification and through the OCR-based classification. The only difference was that along with the prediction, it would give us a confidence score. And the final prediction would depend on the value of this confidence score. Using that, we were further able to increase the test accuracy to 88.29%. But there were certain boundaries which were there in sector fingerprinting, which we explored after we built our classifier. The first one was that we had some counterintuitive features which were picked up by our classifiers, and which was probably the reason why the test accuracy was slightly lower than 90%. For also the classifier size, because it would be a part of the malware, we saw that the image-based classifier was slightly heavy. So we thought of using the text-based classifier as the lightweight version of our malware. We understand that that would lead to a 4% drop in test accuracy, but we explored each of these sectors and saw that chemical sector always had 100% test accuracy, which meant that if the attacker is able to infect a chemical plant, then the success rate of attack is very, very high. Now that we know about the broader idea of the plant, we delved into a process fingerprinting to know about the more fine-grained idea about the plant. Starting with dataset construction, we looked for PLC codes all over the internet, which was a very difficult task. We looked into Shodan and GitHub to get PLC codes, and we found 69 PLC binaries in the internet, out of which only 52 had useful information, and we could not have used the rest. They belonged to the four critical infrastructures which were helpful to us because our sector fingerprinting also used 3 of these 4 critical infrastructures. Then we analyzed and we saw that these particular PLC binaries belong to 3 processes in general, which were pressure process, temperature process, and timing process. The manual leveling was done using primarily by ICS ref, which is a PLC binary reverse engineering framework, which gives more information about the control variables, the control modules which are used in the code. And secondly, by using strings command in Linux, which gave us more intuition about the comments used in the code. And we also analyzed some metadata like location to find out more about the code, and if and when the source code was available, we analyzed that to understand that what that process did. For finally making a process fingerprinting classifier, we followed the same parallel architecture as we followed in sector fingerprinting. That is, we ran the PLC binary using the strings command and used the text from the strings to classify them as one of the 3 processes, or we ran the PLC binary through ICS ref, which gave us the FB names or functional block names, which are functional modules of a controller code. This actually gave us more semantic information, and when we used this parallel architecture, we were actually able to get 93.33% test accuracy, which was more than 10% higher than what we got if we used either one of these arms. Now that we have an idea of the plant, which is the targeted knowledge of the plant, automatically we need to focus on the final attack vector, which would run the plant into a suboptimal state. The perturbation here is the malicious manipulation, which will actually establish that aim. Before we delve into the specific perturbation-based attacks, let us look into a typical control system, which is there in an ICS. In any control system, the plant is designed to run at a reference value of the process quantity. The reference value is carefully chosen, that the control objective is met and the plant is always running at a profitable level. But it's a physical quantity, and that's why it always deviates from the reference value, giving rise to an error. This error is processed by a controller, what we call as a programmable logic controller, and it is programmed in one of the five PLC programming languages, which is structured text, ladder logic, or functional block diagram. And we choose for our attack one of the common controllers used in the field, which is called a proportional, integral, and derivative controller. These controllers try to manipulate one of the aspects of the error such that the error is minimized. And they do that by using the coefficients or the controller coefficients, which are called Kp, Ki, and Kd respectively. After the controller is designed, the actuating signal is fed to the plant, which tries to lead the plant to an optimal state. But what we want to do as an attack is that we want to run this plant in a suboptimal state, not blow up the plant. And we want to do that by injecting the malicious Kp, Ki, Kd values directly into the binary using ICS ref. For process aware attacks, which is based on the perturbation, we actually designed three such attacks. The first one is what we call as the stable perturbation. Here we represent a stable perturbation by showing the attack objectives. The green line is actually the original reference signal, and the red line is the malicious aimed signal what we want to achieve. The dashed blue lines are the alarm thresholds. So what we want to achieve is an attack vector which is slightly lower than what should be done, but it is within the alarm thresholds. We found that by using integral values and proportional coefficients, we were able to achieve this value. The second one, what we explore, are oscillatory perturbations, where the oscillations will happen within the alarm thresholds. This can be easily utilized to leverage certain mechanical properties like that of a pipe, where the fluid is made to oscillate, thus compromising the integrity of the pipe. This is also done by manipulating the proportional constants of the controller. Finally, the third attack which we design is the physically trigger time attack, which is like a ticking bomb. That is, the attack is actually launched before, and the attacker may escape. The final attack, which is beyond the alarm threshold, is launched after a much later time when the attacker cannot be caught. The process of generating the algorithms for these attacks are discussed in detail in the paper. We performed the entire pipeline of the attack using a hardware in the loop test bed. We developed this hardware in the loop test bed where we use a MATLAB simulation of the Tennessee Eastman process, which has 18 control loops, and we take out two of these control loops and control it using a physical PLC, which we use Vago 750-881 PLC. The sensor values are sensed from the MATLAB benchmark using this PLC, and the actuating signal are again fed back to the MATLAB benchmark. The HMI, which is designed here, is designed using LabVIEW. Now we perform the ICS sector fingerprinting within 3.09 seconds, and we perform the ICS process fingerprinting and intelligence collection using ICS ref as well as the PLC binary in 30.57 seconds. And finally, we ask the malware to give us the attack vectors within the alarm thresholds, and it gives 4 such attack vectors. As we can see that all of these are stable perturbations which continue over a long period of time, and because of these stable perturbations there is an increase in the maintenance cost, as can be seen by the blue dashed line, and the original cost is given by the red dashed line. Thus, in concluding our work, we want to emphasize that since we were able to perform this attack completely, we want to continue the holistic analysis of ICS. And therefore, we want to keep augmenting our database of binaries and HMI screenshots. But we also want to develop defenses against our attack. So we want to explore adversarial examples that can evade automatic fingerprinting using HMI screenshot, but we have to be careful about the usability versus security trade-off. We may choose to disable our FTP connections to not extract the PLC binary anymore, or may choose to insert some random code. Finally, we want to explore process-aware defenses so that our process-aware attacks, which is based on perturbation, can be evaded. With that, I want to thank you all for your interest in our work. Please do not hesitate to reach out to me and check out our lab page and our GitHub page for our resources. Thank you.